Okay, so we're going to talk about Gibbs free energy and equilibrium. Gibbs free energy we will talk about a bunch. But for right now, Gibbs free energy can be defined as the amount of energy available to do work. We use it the most to determine if a reaction is thermodynamically favored. That's the new term. The old term is spontaneous. A spontaneous reaction occurs without any outside intervention. If it is spontaneous, all you have to do is get the particles together and they will react. Okay. If you were to think of chemistry as a kingdom, Gibbs free energy is the king. It is the most powerful indicator of chemically what's going to happen in a chemical reaction. Now, if delta G, which is Gibbs free energy, is a negative quantity, the reaction is spontaneous in the forward direction. So if it's negative, it's going to go without any outside intervention. If delta G is equal to 0, the reaction is at equilibrium. What does that mean? It's happening spontaneously in the forward and in the reverse reaction. You got that? It's not that nothing's happening. And if delta G is positive, the reaction is not spontaneous in the forward direction, but is spontaneous in the reverse reaction. So we said before that every chemical reaction has a tendency to spontaneously proceed to equilibriums. Now, we have talked about this a number of times. Let's recall that at equilibrium, we're not talking about the concentration of the reactants and the concentration of the products to be the same. We're saying at equilibrium, the ratio of the products to the ratio of reactants no longer changes. Recall? Okay. I will be using my favorite reaction when we are talking about this. All right. If I put two things together in a reaction vessel and I find the value of Q, and I find that Q is less than K, I know that the reaction will proceed spontaneously in what direction? Q is less than K. It will go to the right, it will go to the forward direction until it reaches equilibrium. Everybody good there? Spontaneously proceed to the right. The value of delta G would be positive, negative, or 0. Negative. Negative.
So delta G corresponds with Q?
More so, yes, it does.
Okay.
There is mathematical relationship. We're going to use it more often with K, however.
Okay.
If, when we put our reactants together, we figure out that Q is greater than K, what way will the reaction move in order to find equilibrium? It will go to the left. Will that spontaneously proceed to the right? No. So that means that delta G is a positive number. If when I calculate Q, it equals K, delta G's value will be 0. It will be 0. Now, let's look at this graph. I believe your graphs are going to be quite heavily tested on the AP exam. Might be wrong, but here we go. All right, so on our y-axis, we have Gibbs free energy. On the x-axis, we have the progress of reaction. Here we have a mixture that is just pure products. Here we have, pure reactants. Here is just pure products. Okay. Delta G is less than 0 until we hit equilibrium. Did we get this part? All right, and at equilibrium, we will notice that this is the quantity of products to reactants. Are we clear here? This would be the ratio of products to reactants. We can look at the graph that we have been talking about so far, where we had the concentration of reactants and the concentration of products, and this line indicated equilibrium. This would be somewhere past this point. Are we clear there? Okay. And after equilibrium, delta G is greater than 0. What this means is that until we hit equilibrium, delta G will be negative. Well, no, I don't think so. What I think this is saying is, if this is equilibrium and we're not there yet, it will spontaneously move till you get to equilibrium. Okay? And then once you get to equilibrium, it will not go any further unless you do something to it. Okay. Now, the balance between the reactants and the products is determined by the free energy difference between both sides of the arrow. And we will talk about that all the time. How many people remember enthalpy, delta H? You calculated delta H by taking the values of the products and subtracting the value of the reactants. You will do the same thing for delta G as well. Okay. So the greater the difference in free energy, the more the reaction will favor one side or the other. The smaller the difference, the more likely it is that the concentration of reactants and products will be equal. Now, there is an equation that governs the link between Gibbs free energy, scratch out that part please, Gibbs free energy and the equilibrium constant. In chemistry slang, this is delta G is equal to negative rattling. See where it kind of looks like rattling? Okay. Delta G is equal to negative rattling. Where delta G is Gibbs free energy. R is the gas law constant that relates to energy, not the other one. The gas law constant that relates to energy. And T is the temperature in Kelvin as defined by this. Are we good so far? Okay. Now, if I rearrange this equation in order to solve for the equilibrium constant, K is equal to E raised to the negative delta G over RT. Are we good there? We recall that E is the antilog. Yeah, it has a value of about 2.718. You can kind of think of it as like putting pi in an equation. All right. So this is how we would solve for the equilibrium constant. Let's talk about that here. Generally, an exothermic reaction, remember exothermic has to do with the enthalpy of a reaction. Enthalpy of a reaction is delta H. Here is a synonym that you will see on the AP exam because they like this a lot this year. Exothermic is also exergonic. Do not be fooled. Exergonic, exothermic, same thing. If the delta H in an exothermic reaction, positive or negative?
Positive.
Negative. In an exothermic reaction, delta H is negative. That reaction usually has a delta G value that's also negative. In an endothermic, its synonym would be endergonic reaction, delta H is positive, and so is usually delta G. Let's talk about some math. I don't think that you are going to be asked to solve the delta G equals rattling problem. I think what you're going to be asked to do is make generalizations based on the equation. I've rewritten this equation, K is equal to this, and let's talk about it. If delta G is negative, that means this quantity is a positive number. Everybody with me there? This is a positive number. So K is going to be a positive number as well. What does that mean in terms of equilibrium for that reaction? It favors the products. So you see how these are tied to each other. Okay. The larger the value of delta G, the larger the value of K. If in the other case, delta G is a positive number, this quantity will be a negative number, and K will be a smaller number, less than 1 perhaps, and that will mean that the reverse reaction is favored. That means the reactants are favored in equilibrium. Everybody good there? Okay. Now, we were talking previously that the only thing that affects the value, when we're talking about Le Chatelier's principle, the only thing that affects the value of the equilibrium constant is what? Temperature. Okay. I want you to think about this as thermal energy, and the reason why that the temperature is affects the value of K has to do with this equation. The temperature is going to affect this value of K because of this equation. Everybody good there? I can see that somebody might ask you in terms of this equation, if the temperature increases, what happens to K? Can you figure that out? Okay, because the denominator, right, gets bigger. Okay, that's what I would like you to get out of that. All right. Now, this is a huge, huge thing that you just have to stick in your back pocket and know this. If delta G is 0, K is equal to 1. There are going to be times in problems where you solve for delta G and you get that answer, everything is fabulous, you end up with 0, and they ask you what the value of K is. More frequently, they're going to tell you the reaction A plus B yields C plus D is at equilibrium. And then they're going to ask you to solve something else. You must recall then that delta G by definition is 0. Otherwise you're going to end up with 2 variables and you can't solve the problem. If delta G is negative, then K is greater than 1. If delta G is positive, then K is less than 1. Here would be a baby question that I envision that you would be asked. In the reaction A is in equilibrium with B. The equilibrium concentration constant Kp is 2.3 times 10 to the negative 5th. That is less than 1. Which direction is favored here? At equilibrium.
The left.
At equilibrium, there will be more of this than that, correct?
Yeah.
Which way spontaneous, is delta G going to be positive or negative?
Positive.
Positive, a positive number. Okay. Now, more graphs for you on the next page. All right. I'm still talking about this reaction that has this equilibrium constant, okay? And let's look at these 3 graphs. It's asking you which one of these graphs depicts what will happen. And here we have the first graph. We're on the y-axis, it's Gibbs free energy. Here is the extent of the reaction. Here we have pure A. Here we have pure B. And they're saying when equilibrium occurs, how do you know where equilibrium is? The lowest point on this graph is where equilibrium will be. The lowest point is where equilibrium will be. Okay. When that occurs, will there be more B, or will there be more A? There will be more A, so this does not depict an equilibrium constant that's less than 1. This would depict, since the low point looks like it's halfway between A and B, this would be at equilibrium, yes? Okay, so that's not it either. And then we have this graph, where at equilibrium we are closer to the A value than we are the B value. So this would be the correct graph depicting that equilibrium constant and Gibbs free energy, yes.
So because it's closer to A, it favors the reaction.
Yes, yes.
Which one is right?
This is the correct one, the last one, because it's closer to A. It looks like it got cut off right here. All right, the next question is a plug and chug, and I'm going to leave you to figure it out on your own. Here is something that you can learn from first period. Delta G is customarily given in kilojoules. R is joules. Convert back and forth. Okay, that's where we stop with notes, and then let me stop this from recording, and then we'll talk some more.